Hi, and welcome to this presentation in which we're going to introduce the concepts of error and bias. And so let's start by reminding ourselves what we are doing when we do epidemiology. And that is, it's a game of measurement. We're wanting to know whether or not someone or something has disease. We want to know about exposures, and we're trying to measure those values in a population. And we want to do it with as little error as possible. And this error can creep in the form of bias, which is when our measure of disease frequency or effect, so our incidence rates, our incident rate ratios, odds ratios, differ in a way that is systematic from the true value. The other sort of error that can creep in is something called random error, and that's really relating to the variability that is due to sampling. Okay, and if we think about them, a useful way to consider it is that as our study size increases, our random error will in fact go down. So this is this blue line here. So in other words, the bigger your study gets, the less error there is due to random error in that study. In contrast with systematic errors, so for example, you haven't used probabilistic methods to sample from your population, or you're not measuring with a very good diagnostic test, well, that error is going to exist no matter how big the study gets, and it's not going to be changed in any way by the study size. In fact, all that happens when you do a bigger study with a lot of systematic error or bias is that you have really just wasted more money. So let's unpack this concept of random error a little bit more, and let's consider a scenario in which you want to know the average litter size from the last 100 sows that farrowed on a farm. And this information is presented here in a histogram, and you can see that the peak of the histogram is around 11 to 13 litters, piglets in the litter, and it's reflected here in the mean being 12, and the standard deviation, which is just a measure of spread, is 3.04. So it's basically saying 12 plus or minus about 3.04. All right, now if we went in and just sampled from the data that we had about that, and we just said, okay, I'm going to randomly sample 5 sows and record their litter size, then we might get something like we have here, where we have 12, 10, 12, 13, 11, and we're estimating an average of 11.6 with a standard deviation of 1.1. So our estimate of the average litter size is a little bit smaller than the truth. We could go on and we could take another 4 random samples so that we in total will have 5 random samples, and you can see here purely by chance that the average that is estimated ranges from 11.16 to 13, 9.2, 12.6 and 12.6. So we get 2 that are almost identical there in terms of average. All right, so the more samples we have in that case, so if we were to sample all 100 of them, then the better our estimate is, the greater the precision. And so this precision that we're talking about is these 95% confidence intervals that I can put around an estimate. So the more samples we have there, the tighter those confidence intervals will be, and the more faith we have that as to where the truth lies. And so what a lot of people will call this, because it's due to random sampling, is chance. The chance is playing a role in our studies, and all we know is that if we sample more, we reduce the random error. Now, the other types of problems that creep into studies are bias. And the main forms of bias are selection bias, and that occurs because we end up with a distortion of our estimate, be it the incidence of disease or an odds ratio, due to how we enrolled our subjects. Another form could be information bias, and that's a distortion of the estimate due to the inaccuracy in the measurement of the study outcome. So we might have used, for example, a very poor test. And then the final source of bias could be confounding, and that's a distortion of the estimate of effect size. And it really does, and we'll come back to why this is the case. We really can only talk about confounding when we're talking about estimates of effect size, so odds ratios, incident rate ratios. And it's when that estimate is incorrect due to another factor, a third variable. And so again, just to reiterate the main differences between random error and systematic error or bias, is that systematic error or bias remains exactly the same no matter how big the study is. So if you have a crap test, it's a crap test whether you sample 10 people or whether you sample 100 people. In contrast, however, your random error, that chance of the estimate, will in fact start to decrease the bigger the sample size. So in the next 3 presentations, we're going to unpack each of the 3 main causes of bias or systematic error.